we will see what is an electric field. Now, every charge will create its own field around it. Suppose there is a positively charged body. Around the charged body, there is a field everywhere. What do you mean by that field? Field is the region where another charge will experience a force. For example, around the Earth, suppose you assume that Earth is a spherical body, then around the Earth there is a gravitational field. You can't see that. You can just draw the diagram showing that there is a field in many ways, but there you can't see it. Now you can feel it. How can you feel it? Any mass in this universe produces a gravitational field. And if you want to test it, you have to take another mass which can experience it. So if you want to test a field, you have to take another particle or another such a type of charge or a mass which can experience that field. So take a ball of a very small mass compared to the mass of the Earth. Leave it, and that ball experiences a force and comes downwards. And if you take the ball far away, it will experience a different amount of force and it comes down. So these forces will tell you that there is a gravitational field everywhere. So can I can say that gravitational field is the region wherever another ball experiences force. And if you take the same ball to the Jupiter and do the same experiment, then you will feel that the ball may experience more and more force at the same heights in the Jupiter, saying that the field around Jupiter will be stronger than that around the Earth. So in the same way, even if you take a bulb for that matter, suppose you have a bulb. If it is switched on, then it will create its own luminous field around it. What do you mean by luminous field? It will create its own light and it will emit light, and that light travels from the filament of the bulb in all the directions. Now, how to test whether there is a field due to this, a luminous field due to this bulb everywhere? Take a small piece of paper and keep it here. If light falls on this, then I can say that there is a field here. Similarly, if you take the paper and keep it somewhere here, then the amount of light falling on this will be less. So there is a field, but it is lesser than that at this point. So there is a luminous field around a bulb. There is a gravitational field around a mass or Earth or a planet. There is a electric field around a charge, and there is a magnetic field around a magnet, so on. So we measure that in terms of a field. For example, we say cricket field. What do you mean by cricket field? Cricket field is a region where players play the cricket. You can see the cricket in that field. So there is a boundary for it. Similarly, charge will produce its own field. Now, how to test that strength of the strength of the field or the direction of the field? Because electric field should be a vector quantity. It should have some directions. So, how to measure that? In order to measure the strength of the field around a charge, you have to bring another charge, and that charge is called test charge. Now, let me keep a very small positive charge here in order to test it. So if you want to see that there is a gravitational field around Earth, take a small ball. Then compared to the mass of the ball, mass of the Earth is very high. So the ball itself moves towards the center of the Earth. So there is a gravitational field here. Similarly, you take a test charge. The test charge should be so small that it shouldn't affect the field of this positive charge. I call this as source charge, the charge which produces the field, and I call this as test charge. So this is a tester, and this is the one which produces the field. So now that test charge shouldn't affect the already present field here, right? So you use a stethoscope for measuring the heartbeat. But when you keep the stethoscope on the heart, the usual heartbeat shouldn't change. So stethoscope should be such a smooth instrument that when it is kept on the chest of the patient shouldn't feel anything different. So the normal that heartbeat should remain the same. And moreover, the existing field shouldn't change when the test charge is kept. Sir, what should be the value of the test charge? Usually, test charge is taken as a unit positive charge, plus 1 coulomb. Sir, it should be always plus 1 coulomb? Need not be. It can be anything. But when you write the definition, you should take plus 1 coulomb. So, test charge is unit positive charge. So what do you mean by unit positive charge? It is plus 1 coulomb. So this is taken as a notation or a conventional charge, and this is always used to measure the strength of the field. Sir, now how to measure the strength of the field? How do you measure the strength of the field? Suppose you have a charge source charge. I will show it is in red color. Suppose this is a source charge and it is creating field everywhere. I select a point at a certain distance from the source charge here. So it produces field everywhere, as if you switch on a bulb, what is the amount of light here, what is the amount of light here, what is the amount of light very close to the bulb, as you measure it. I select a point here, point P, and if I want to see what is the amount of field here, I have to take a test charge which will experience this field. Suppose if I keep a ball here, it won't experience any force because a simple neutral ball cannot react with the electric field. A new ball can react with the gravitational field because it can produce its own gravitational field. It can react with another gravitational field. So I have to keep a charge here. I keep a charge Q. Sir, won't you place unit positive charge? I will tell you why it is unit positive charge. And now I will place at the point P a small charge Q. It is not unit positive charge. But definition says like this. What do you mean by electric field at this point? Electric field at any point due to a source charge is the force that this test charge would experience when placed at that point. Now coming back to this Earth's example here. Suppose you want to measure what is the strength of the gravitational field here. You place a ball and let us assume that ball is a living object. You ask the ball, how much force you are experiencing here? Ball will tell you, sir, I am experiencing this much amount of force. Say this height is 10 meters. Take the same ball to a height of 10 meters on the Jupiter. Ask the same ball, how is the situation now? Ball will tell you, sir, the force is much more than the force that I experience on the earth. So force is different. So you have to take an object which can feel that field. So we have taken a test charge. It is also a charge. So test charge is always positive. But now I have taken some value of charge Q, small q, and let this source charge be capital Q. Okay, let this be capital Q. Now, according to the definition, electric field is nothing but the force that a test charge would experience when placed at that point. It is like a stethoscope. Wherever you want to measure the field, you place that test charge. Sir, I want to measure the field here. Place that test charge here. Ask the test charge. How are you experiencing the force? What is the direction? What is the amount? And what is your value? Force per charge, force per that test charge kept at a point is called electric field. But actual definition goes like this. Electric field at any point that is defined as the force that a unit positive charge would experience at that point. Sir, why do you restrict it to unit positive charge? Whatever the charge you keep here, final answer will be the force that a unit positive charge would experience. I will explain it, how it is so. So, electric field at any point in a space produced by a source charge is equal or is defined as the force that a unit positive charge would experience when placed at that point. Sir, why it is so? Now, I will place a charge of 2 coulomb here. I ask that 2 coulomb. So, this is a source charge and its value is Q. I am not worried about the capital Q here. I want the electric field here, the strength of the field here. Now, I will place 2 coulomb here. I will ask the 2 coulomb. 2 coulomb, how much force you are experiencing? 2 coulomb says, sir, I am experiencing a force of 6 newtons, sir. So what is the electric field here? If I calculate it, electric field is 6 Newton force experienced by 2 coulomb, F by Q. What is the answer? 3 Newton per coulomb. This is the answer. Okay, I can measure the heartbeat of a patient using different stethoscopes. Remember, heartbeat of a patient doesn't depend on the type of stethoscope you used. Heartbeat of a patient depends on his heart because it is the source for the heartbeat is his heart. You shouldn't finally conclude that, oh, if heartbeat had been measured by another stethoscope, I would have got a very good result. No, it is not possible because heartbeat depends on the heart. It does not depend on the stethoscope. Okay, so this is 3 Newton per coulomb now. I will place now a different charge. I will place some 3 coulomb here. That is my test charge now. When I place 3 coulomb here, ask the 3 coulomb, how is the situation? What is the amount of force that you experience? 3 coulomb says, sir, I am experiencing 9 Newton force, sir. So what is the electric field there? 9 Newton force experienced by 3 coulomb. Answer is 3 Newton per coulomb. Same answer. if you place, in order to measure the field here, if you place a stronger charge, you will experience stronger charge will experience a stronger force, and answer will be the same. If you place a 4 coulomb here and try to find out what is the field, 4 coulomb will say, sir, I have experienced a force of 12 Newton and this is 4 coulomb, and answer is 3 Newton per coulomb. Answer is same. Now you place test charge as unit positive charge. What will be the answer? You ask the unit positive charge. Keep 1 coulomb here. Unit means 1 coulomb charge here as a test charge. Ask him. Unit positive charge, how much force you are experiencing here? Unit positive charge will say, sir, I am experiencing only 3 Newton force here, and the charge is Q is 1 coulomb. Answer is 3 Newton per coulomb. This is the answer. Now you see, out of all the forces, you see, this force F by Q, this is not the answer. 3 is the answer. This force 9 is not equal to 3. 12 is not equal to 3. But here you see, 3 is equal to 3. That means what force that unit positive charge will experience, same amount of electric field we get. That's why the definition goes like that. Electric field at any point is the force itself that a unit positive charge would experience when placed at that point. Of course, it is here you can't say, is for example, when 3 coulomb is kept, you can't say electric field at a point is the force, because 9 is not the final answer, which is the force experienced by 3 coulomb. No, it is it is the force experienced. Here 9 Newton is not the answer here. So electric field itself is not 9 Newton per coulomb. So electric field will be the force itself when you keep 1 coulomb charge, unit positive charge here. So electric field at any point in a field, at any point due to a source charge, is the force that a unit positive charge would experience when placed at that point. So for definition you can take unit positive charge, but while practically doing it, of course it is not so easy to do practically, but practically when you do it, it is the answer is the force experienced by a unit positive charge. Okay, now coming to the quantity. Sir, whether electric field is a vector or a scalar? Definitely it is a vector, because this force has a direction. Charge is a scalar, we know it. So what is the direction of electric field? It is the direction along which force acts on the test charge. So what is the direction of electric field here? This test charge would experience a force like this. So I can write electric field like this. Okay, so electric field is a vector quantity. Its direction is same as that as the force experienced by a unit positive charge. Now, what is the SI unit of electric field? Very simple. Look into the formula and you not by heart it. Simply remember electric field as the force experienced by a unit positive charge kept at a point. And remember, if you usually forget the definition, you do one thing here. See, in the alphabetical order, you get electric field E, force F. Alphabetical order, after E, you get F. So if you are asked to define electric field starts with E. What is after E in the alphabetical order? F. So if that is force. So electric field is force experienced by a charge, because you will get another definition in future that is called potential. So potential at any point is the work done in taking the charge. So how to remember this? You see, in the alphabetical order, after V, you get W. Potential at any point is the work done per charge kept at a point. So this is the definition. So if you are asked potential, symbol is V. After V, you get W. So start from work. Here start from force. Force that a unit positive charge would experience when placed at that point. So whenever you want to find out the electric field at any point, keep on placing a unit positive charge at that point and try to find out the field. So from here onwards in this chapter, wherever is electric field is asked, you must have a unit positive charge in your pocket or a test charge in your pocket. Always keep it in a pocket, as if doctors always keep stethoscope with them. An electrician will always keep a small tester with him. So similarly, being a science student and studying physics, the first chapter electric field, as long as the first chapter is going on, keep a test charge in your pocket always, because whenever you get a chance of measuring the test charge, simply keep that test charge there. Ask the test charge how much force it is experiencing. Then force by charge, that gives the answer. Or if you have a unit positive charge, that force itself is the answer. So that's how we define electric field, and it's a vector quantity. Its unit is Newton per coulomb. Okay, Now, suppose you are asked to write the dimension for electric field, and it is very simple. And always, whenever dimension for charge is asked, usually we define a dimension for this length, mass, and time. There is no dimension for current or current. You will get a definition. Usually you have studied in, most probably you have studied in current in your 10th standard. What is current? Current is nothing but rate of flow of charges, delta Q by delta T. The small amount of charges flowing per second in a conductor. That is called current. So whenever in electric field, potential, capacitors chapter, you get a chance of writing the dimensions. What you have to do is, whenever you get a charge, just turn it as current into time. So shall I write the charge flowing is current into the time? So whenever you get a charge, write the dimension as, so dimension of charge is equal to ampere. Actually there is no dimension for current, but I will take it as A, and time is T. Okay. Now if it is so this should be ready with you always, right? Because so many times we get the quantity charge. So charge dimension is A into T. It is I into current into time. Now, if you are asked to write the dimension for electric field, what you will do? So write the formula for electric field. It will be E, only dimension wise I will write, only no vector form, only magnitude. Now E, F is, I can write F as mass into acceleration, right? MA. So if you want to write the dimension of electric field, dimension of force, dimension of charge, MA, and here I can write is that current into time. Now what is M? Mass. So M, acceleration, LT to the power minus 2, and what about this one? Current is ampere into time. So this is the dimension. Okay, you can rearrange it. After rearranging, what you will get? So that is equal to M. I can put the square bracket because dimensions have to be written in the square bracket. M and L, then T to the power minus 3. ML T to the power minus 3. Here you have a 1. When it comes to the numerator, minus 1. So total minus 3. Ampere to the power minus 1. Right? I will adjust the space. Minus 1 here. So L T to the power minus 3 and ampere to the power minus 1. This is the dimension. So that's about electric field.